I skip the first part where I thank the organizers and come to the problem. So, and let me recall you the notion of the bistability. Of course, all you know, but nevertheless, let me recall it. The paradigm model, so the classical bistability is a nonlinear driven oscillator which is subject to friction. And you can find this problem in the first volume of the Landau-Lifshitz and Mechanica, which is very, very old problem. And the point is that unlike the linear dissipative oscillator, this is red curve, which shows the amplitude of the oscillator as a function of the driving frequency. So nonlinear oscillator may shows the bistability, which means that at some values of the frequencies, driving frequency, like here, you have two solutions of this equation, Hamiltonian equation of motion plus frictions. So the one is with high amplitude, which I shall refer to as a upper limit cycle, and the second one with very low amplitude, which is a lower limit cycle. What solutions is realized in practice depends on the initial condition. And this is like this one. So if you are in the, for example, this one, I guess it is for nu equal somewhere here. So if you are in the yellow regions, you will be attracted to the upper limit cycle. If you are in the blue area, you will be attracted to the lower limit cycle. The trajectory will be attracted to the lower limit cycle. So essentially what shows this figure, this is the basins of the attractors in the rotating frame for two different driving frequencies, somewhere here and somewhere here. If you choose in between, then in fact you will observe a patterns which resemble very much the Korean national flag, which symbolizes, okay, you can ask our Korean colleagues what is symbolized, but now you see that in fact it shows the attractor basins for the driven nonlinear oscillator. So this is the system. Okay, symbolized driven dissipative. Okay, now about the quantum dynamics of this system. So it is also old problem, but not so old as the previous one. So the studies, I guess this is the first paper. This is two guys, New Zealand scientists, who first addressed this problem, so the quantum dissipative and driven oscillator. And this is what we have. So this is the quantum Hamiltonian of the driven nonlinear oscillator. A, dagger, and A is the creation and annihilation bosonic operator. This is simple stuff, but then you have to introduce the friction. And one do this by coupling the quantum oscillator with the Markovian reservoir. Then after eliminating the path degree of freedom, you come to this master equation for the density matrix of our system. This is first part in the Hamiltonian evolution, and the second part is the so-called limb-lat relaxation terms, and it is easy to get convinced that it ensures, in the absence of the driving, it will ensure the relaxation of the operator in the ground state, only in the absence of the driving. As soon as you include the driving, the problem becomes more involved, but still can be solved.
So is this master equation is for zero temperature?
Oh, no. In fact, for zero temperature, you will not get the Markovian reservoir. But the point is only like this one, that you need something which forces your oscillator relax to the ground states.
Okay, but I cannot see any like terms associated with like number of photons in the thermal reservoir.
Yes, so, well, in this case, let's treat it like the zero temperature, because you can write the different relaxation operators which ensure, I mean, that the oscillator will relax not to the ground state, but something different. Okay. Let's consider it's like the zero temperature. also it's hard to derive, to have Markovian reservoir for 0 temperature. Okay, so next step is to solve this master equation, and the standard approach is to use the so-called super-operator approach. This equation is actually all equations in the quantum mechanics are linear. So we can rewrite this master equation in this form, where this capital lambda is sometimes referred to as a super-operator, sometimes as a quantum Liouvillean, but one can easily construct it, even in computer. Then you, because it is a linear operator, you diagonalize it, it finds the eigenvectors, let's say eigenmatrices and eigenvalues. And then to present the general solutions of equation, your master equation as the sum linear combination of these eigenmatrices. So and here comes surprise that because among these eigenvalues, only the first one, lambda 0, is 0. Oh, and this is a steady state solution of the systems. The all other lambda is, has a negative real part, which ensures that they decay with time. So we come to conclusion that quantum-driven dissipative oscillator has only one solution, not two, but one. Then it took some time to resolve these obvious contradictions between the quantum and classical results. I cite only a few papers. In fact, their publications were contingent, and even I, let's say, added my 5 cents to this problem. In fact, it was first written as a tutorial for the students, but then I decided to publish it as a preprint. In particular, to display the basins of the attractors, which looks like the Korean national flag. Well, now comes the motivation for this talk. So, as there are systems which are as simple as a driven oscillator, driven dissipative oscillation, but from which we can learn more than we already know. And this is one of these systems. This is so-called double resonance model. And it is classical Hamiltonian. And this is I simply use a trigonometric equation to put these terms as a sum of two terms. And you may think about the physical realization of the double resonance model as a magnetic dipole, just arrow of the compass, in the alternating magnetic field. Then the Hamiltonian will be angular momentum of the compass arrow, divided by the inertial momentum, and his magnetic dipole momentum and magnetic field, B at T, scalar product. When you take this scalar product, it gives you cosine theta, and cosine nu t is already present in B at T. This is time dependence of our alternating magnetic field. The other realizations, which is now quantum, it is a dipole molecule. This is the same, angular momentum divided by inertial momentum. Now the electric dipole moment and electric field alternating. This is two simplest realization of the double resonance model. I also want to stress that in the rational literature, this model also referred to as two interacting nonlinear resonances. Why it is a name? Because it comes from the analysis of the phase space structure of this system. So this is phase structure. This is the Hamiltonian case when gamma is 0, and this is Poincare cross sections of this Hamiltonian, and you clearly hear these two nonlinear resonances. One is exactly at plus, at plus nu, the other one at minus nu. So this is the position of the nonlinear resonances. And the crucial stuff is how far these resonances are one from another. When they are far from another, then I essentially isolate it. There is mutual effect on one resonance on the other one, and in this case it appears as the secondary resonances which appears here. Now we add dissipation. Gamma is not equal to 0. Then this nonlinear resonances converts in the simple attractor, This is this point, this one to this simple attractor, this point, this to the attractor of the period to these points. And this recolor are the basins of these attractors. Again, if you start from yellow, you come here. If you start from blue, you come here. If you start from this dark green, and this is bright green, you come to this or this.
This is strong enough dissipation or free arbitrary weak dissipation?
Arbitrary. What essentially changes, not the attractor itself, but the basins of the attractor when you change the dissipation. Okay, let's continue with these colorful figures. This is what happens if we decrease the driving frequency. So you see that in the Hamiltonian case, there appears chaotic C with two stability islands here and here, and also remnants of these secondary resonances. Again, when you switch dissipations, you have four attractors and basins. And now you will see that basins of the attractors start to acquire a fractal structure. This is the effect of the, let's say, dissipative manifestation of the chaotic dynamics of the Hamiltonian system. So if we even decrease further, so now it's nice figure. So all secondary resonances disappears. You have chaotic C, two nonlinear resonances with dissipation. It's like this one, and here you clearly see that the attractor basins are fractals. And perhaps also the last figure, no, the two last. So if I start to decrease the driving frequency further, I mean, these two attractors shows a cascade of bifurcation. For example, here you see the appearance of the attractor of the period 3. This is 3 points which originated from these attractors. And finally, it results in the chaotic attractor. Everything is attracted to the chaotic attractor. So you see that the simplest is richer than nonlinear driven oscillator, but in the limit of the large driving frequency, in fact, is simpler. So when we use this opportunity to find the to obtain some analytical estimates.
We have a question.
Is this system is conservative or dissipative?
Dissipative. I mean, to the left is Hamiltonian, to the right is dissipative.
Okay.
It is what was up for all figures which I have shown. Okay, so essentially we do the same as for the driven nonlinear oscillator. We construct the superoperator, but now because the system is explicitly time dependent, it will be Floquet superoperator. So you do this stuff, and then you diagonalize it and find the eigenvalues and eigenmatrices. Because this is now Floquet operator, this one, lambda 0 is not 0 but unity. This is the point, that it corresponds to the true steady state solution of the system. Okay, and this is the spectrum as the function of the driving. Sorry, that should be new. This is the driving frequency. So our interest will be the first three levels, eigenvalues. The first one is of course, this is 1. This is lambda 0, then lambda 1 and lambda 2. Which in these regions are degenerate or practically degenerate, but then start to deviate one from other. And of course, this is large lambda. It is easy to understand that these two eigenvalues are responsible for the two resonances in the upper and lower part of the half plane. Okay, so let's now study this. Now I show this eigenfunction explicitly. So now I am studying this case of large driving frequency when you have two resonances here and here, or let's say these basis on attractors look like this one, and this is the diagonal elements of the first three eigenmatrices, 1, 2, 3. And you immediately can identify the first one, which is the ground state, steady state, true steady states of the system. It is, you see, around 0. Then this one is somehow symmetric combination, asymmetric combination of this and this. This one is symmetric combination of this plus this. But the point is that they are enough to take the linear combinations of them, which is located, in this case, exactly at the upper nonlinear resonances. Then, because these two are degenerate, lambda 1 and lambda 2, in the course of revolutions, this will die out and you will stay with this one, which is this one, relaxation. Of course, then you see that these resonances have a finite lifetime. And I mean, in terms of the previous figures, this lifetime will be determined by this gap between this line and the upper line. This is lifetime. But because of this simple structure, we can obtain an analytical estimate for the lifetimes of the nonlinear resonance. And this is the estimate. So look. So first, I now consider only one resonance. I introduce the notion of the local basins of the attractor. And this is the separatrix trajectory of this effective Hamiltonian. So note that it's a Wolf gamma, and then obtain these estimates. It resembles very much the usual equation for the tunneling. But note that this is dissipative system. So it is not the Schrödinger equation, this equation shows the master students. And the gamma, it goes here, and it's also present here due to these terms. No, this is which defines you the area S below this separatrix trajectory. And this is the analytical estimate for the lifetime for the metastable quantum attractors, if you wish, like this one. This is lifetime. Okay, so this is one result. Now come to the house assistant tunneling. What's hot topic some times ago. And it was discussed within the framework of the Hamiltonian system, like this one. So in the classical case, if you put particles in this nonlinear resonance, it will stay here forever. But if you address this problem quantum mechanically, it can tunnel from one stability island to the other one. And this tunneling is in fact enhanced due to the presence of the chaotic components. There are some authors who studies this problem. This reference who refers to the Mike Risen. This is experimental paper who studies this house assistant tunneling in the experiment. But I address the question about the tunneling in the case of the dissipative system. So in classical case, this is the same situations. If the system is attracted to this limit cycle, it stays here forever. But in the quantum case, it can tunnel to this one. Yes. I have two slides to show. And to understand when this tunneling is happened, in fact, we should simply follow the eigenvalues which corresponds to the steady state to this blue line. So this shows for difference value of the driver frequency. This is the case of the large one. As I said before, in this case, the steady state of the system is that everything is around zero. When you start moving these directions, you see that it changes this one. There appears some remnants. When we come to this value, it is 3. No, this is 1.6, 1.6 here. I mean, these states is like this one. And this is the steady states of the systems. It means that quantum mechanically, the system has equal probability to be in the upper and the lower limit cycle. And even if you prepared your initial conditions in such a way that initially you are in the upper limit cycle, it's very quickly relax to these situations. And this is again, time is defined in terms of this gap between these. And in comparison with the case of the Hauss-assisted tunneling, it is enhanced by the order of the magnitude. In some sense, the dissipation enhances the Hauss-assisted tunneling by several orders of the magnitude. Conclusions. Okay, this is just a repeat that this system is, on the one hand, is richer than the driven dissipative oscillator, on the other hand, simpler. Because it's simpler, we get analytical estimate for the lifetime of the quantum limit cycle. But for solid it is richer than the nonlinear oscillator, and we address the novel phenomena as a dissipation. This is what was added to the Hauss-assisted tunneling. That's all. Yes, I didn't discuss the transition to the chaotic attractor. This is open question. And reference.
Thank you very much for this nice talk. Yeah, we have time for questions.
I want to ask, you told that there is no way in classical regime to get from one attractor to another. But there is Kramer's problem, and if your system is noisy, then you can get activated through the unstable stationary point or whatever, and
come to the other attractor.
What?
Yes.
So my question is, you have obviously both phenomena, and to the best of my knowledge, nobody knows how in general to combine activation with tunneling. So, but at least can you give a criterion under which condition activation wins, under which condition tunneling wins?
Okay, I would not even call this tunneling. So it was, let's say, the marketing. Okay. But your physical intuition is correct, absolutely correct. So the point is that because everything is done in terms of the master equations, which has this term, and also it's responsible for the dissipation in the system. It's because it relates to the ground states. So when you treat it correctly, I mean, rewrite it in terms of the Wigner function, you will see that there you will get a weak diffusive term, which is proportional to gamma. And in the classical representations, you let's say, reduce this master equation to the Fokker-Planck equation with this diffusion term. Then, let's say, substituting the mark, putting into correspondence to this Fokker-Planck equation, the Langevin equation, you get the classical noise. And indeed, so if you simply use this simple fact that there is weak noise, then it might be enough to kick out the system from the basins of this attractor to the blue region, and then it will attract to this one. So in some sense, I do not know.
You don't have quantitative criteria. I should recall that
yes. You should compare the, let's say, local basins of attractors with intensity of this, I would say, irreducible quantum noise. Is it okay?
I will show you a similar problem where the same thing happens.
Okay, good.
Okay, we still have time for an additional question.
Yeah, so if you go to the Lindblad equation, I had a question. So suppose you want to have, so maybe you mentioned this. So suppose you want to have, explicit role of temperature. You can, I mean, this term is actually gamma times n bar plus 1, and then you have a term gamma n bar times the other thing. So if you add the term, what happens? I mean, or do you expect something different, or you?
Well, of course, then everything is mirrored, because if you add the term like this one, this diffusive term, which we just talked with the Boris, so it becomes proportional not to gamma, but to gamma multiplied by n.
Exactly.
By n. And then you can imagine that then the system will simply behave classically, like the classical system under the classical noise.
Okay.
Thanks. Maybe we still have time for one quick question, if any. Okay, if not, we can thanks Andrey again, and